אוקיי, אז בעצם הוובינר הזה אני מארח למעשה את מר אלברטו פררי, שהוא גורו עולמי בתחום של פאור בי איי ודאקס. הוא יעביר לנו הרצאה בנושא של יחסים בין טבלאות במודל הנתונים ופתרון של בעיית יחסים דו-כיווניים. אלברטו, כמו שאמרתי, הוא גורו עולמי שכתב, כמו שאתם רואים, הרבה ספרים, והוא מרצה למעשה ויועץ בעניינים של פאור בי איי, ולמעשה הוא מסתובב בכל העולם. בתקופה האחרונה הוא פחות הסתובב, קצת יצא לנו לדבר לפני הוובינר, אולי שמעתם חלק מהשיחה, בחור מאוד מאוד נחמד, ומכיוון שכרגע אסור לטוס, אז בעצם הוא כרגע עוסק בכתיבה ובתכנים ופיתוח של תכנים מסוימים. דקה אחת, אני רוצה... אוקיי, ואני רוצה בעצם... זה האתר של אלברטו ושל מרקו רוסו, שהם בעצם שני גורואים עולמיים, חבר'ה שבאים מאיטליה, אתם גם תשמעו את המבצע האיטלקי המתגלגל שלהם, היפהפה לטעמי, וזה האתר שלהם, אתר שהוא כולו בנושא של מאסטרינג דאקס. יש להם פה קורסים וספרים ווידאוים ומאמרים, והם פשוט, זה פשוט, מי שבתחום הזה זה פשוט אוצר. אני חושב שמי שמתעסק בפאור בי איי, אין מצב שהוא לא מכיר אותם, ובעצם הגיע לאתר שלהם. ובקטנה, ממש בקטנה, זה האתר שלי, אתם מוזמנים גם כן להגיע לפה, גם פה יש פה כל מיני דברים, אתם מוזמנים להגיע ולצפות ולהיות בקשר, וגם, אוי סליחה, זה לא דקה אחת, והוובינר הזה בעצם הוובינר הזה בעצם יעלה לתוך הערוץ שלי, לתוך פאור בי איי ישראל, כמו כל הוובינרים האחרים, בעצם ההקלטה שלו תעלה לפה. כרגע זה משודר בפייסבוק לייב, ואני כרגע אעשה stop sharing, and I want to say hello and good evening to Mr. Alberto Ferrari.
Hello.
First of all, thank you for joining me to the webinar. We've got a lot of people registered to this webinar. You know, you are famous in the area of Power BI and DAX. You and your partner, Mark Russo. I'll start telling the audience a little background on you and your website, or your wonderful website and your books. And I'm passing the mic to you. Okay, so
okay.
I will give you the host.
Well, I can already share the screen, so
yeah.
If you see my screen now, we are fine.
Yeah, I can.
Okay. So I guess we can start.
Go ahead.
Welcome, everybody. I'm Alberto Ferrari. Tonight we're going to talk about relationships in Power BI. I'm not going to tell you what a relationship is. We'll go very quickly about the basics about relationships. But before that, what I want to highlight is the fact that relationships, like nearly everything in Power BI and in the DAX language, are simple things, but they hide some secrets. There are several details that you need to be aware of when working with relationships. Failing to know these details or forgetting small details is going to lead to wrong calculations and strange behaviors. And that's exactly the topic of tonight, is not to understand how to create a relationship. I take it for granted, everybody can do that. Instead, I want to show you what can go wrong if you don't know these details. Now, before that, just a few words. I'm going to be very short on that about who I am. I'm Alberto Ferrari. I work with Marco Russo at SQLBI.com. And what we do is basically teaching, mentoring, and consulting about the DAX language and analysis services and Power BI. We wrote the Definite Guide to DAX. We do a lot of courses, and we do consulting. We basically work in the DAX world, trying to teach everybody to use this beautiful language. And that's enough. I'm not here to sell myself. So as I said, first of all, we run very quickly on the basic concepts about relationship, just in order to set up the correct terminology for things. So we will understand, but that will be very short, of what cardinality is, what cross-filter direction is, and what might change, how you set up relationship the right way. And then we'll dive directly in the problems you might face using relationships. So if a relationship is invalid, we understand what happens. We'll discover what the blank row is and the calculations that you need to be aware of because of the presence of the blank row. We'll talk briefly about ambiguity, about circular dependencies, and then we'll talk about weak relationships and calculations at the correct granularity. The takeaway of the entire session is quite simple. Do not use a feature unless you understand really well what it is. There are a lot of features in Power BI. They are there to be used, but before using them, you need to learn how to use them. Just using a feature because it's cool is a very easy way to create issues and have models that basically compute the wrong results for no reason. That was enough for an introduction, so let's dive straight into the topic. What is a relationship? I guess everybody knows that. You have two tables like product and sales, and you can relate them. You can build a link between the two tables, creating a relationship. This yellow line at the bottom in the middle. Here, the relationship is based on product key because a relationship always links two tables based on one column only. Speaking about names, we always have the source of a relationship and the related table. The relationship, I think of the relationship as going from the source to the related table. The related table is what we call the one side of a relationship, and the source is the many side. Why do we use these names? Because for one product, there are multiple sales, whereas for one sale, there is only one product. So product is on the one side because there is always one product only. Sales is on the many side because there may be 0, 1, or many sales all in the same place. And then we have the cardinality of relationship that is highlighted as a number, 1 for the one side and star for the many side. And finally, we have this really tiny arrow here in the middle of the relationship, which indicates the propagation of the filtering. The arrow points from product to sales, indicating that if you place a filter on product, that filter is moved from product to sales. Whereas if you place a filter on sales, that filter is not propagated to product because it will go against this tiny arrow. So this is the cross-filter direction. You can change it, and as we are going to see, this is one of the worst things that you can do to your model. But let's do one step at a time. So speaking about names, relationships have a cardinality, the one side and the many side. On the one side, the column need to have unique values, or if you are used to SQL, it need to be a primary key for the table. And it's the one side is also the source for the propagation of the filter context. A filter placed on the one side is automatically propagated to the many side. On the many side, on the other hand, the column may and typically contains a lot of duplicates because for one sale you have a lot of, one product, you have a lot of sales, so the product key will be duplicated multiple times. And it's the target for filter context propagation. The filter context does not propagate from the many side to the one side. It only goes from the one to the many side, unless you ask to do that. You can change the propagation of the filter context using the cross-filter direction. It can be single or both. We'll talk about that later, so no need to go further on that. Last slide about names. There are three kinds of relationships, one-to-many, one-to-one, and weak relationships. One-to-many relationships are the most common type of relationship, the one that you build in all of your model all the time. You have a table that we call a dimension containing attributes. You have another table we call the fact table, and we build a one-to-many relationship, one product, many sales. One-to-one relationships are quite uncommon. You can have both the side of a relationship to be the one side. It doesn't happen very frequently because two tables linked through a one-to-one relationship, they are basically the same table. Expansion goes both ways, cross-filter goes both ways. Whenever you apply a filter to one table, the other table is filtered to. Typically, when you have a one-to-one relationship, that means you you can probably merge the two tables earlier during ETL steps and make a cleaner model with only one table. And finally, we have weak relationships. Microsoft, for whatever reason, decided to call them many-to-many relationships. They are not many-to-many relationships. They are either weak relationship or many-to-many cross-filter direction relationships. They are a new feature. They are extremely dangerous and complex to use because no table expansion happens, and you can easily compute wrong numbers if you don't use them with the correct care. Anyway, I tried to scare you so far, telling you that there are features that you should be aware of and use with care. Let's start looking at the first of the features that you need to know before using the relationship, which are blank rows. Now, imagine that we have a table, like the one you see on the screen, where we have amount, just the amount sold, and the product ID, the key of the product which is being sold. The product ID has some values, and it's just an ID. Therefore, it's very likely that we want to create another table containing the product ID and all the attributes of the product. And you can easily say we are Italian, but what we consider product, coffee, pasta, and tomato, and nothing else. And we have product ID on one side, product ID on the other side. It's likely we want to build a relationship between the two. And you can do that with Power BI. The problem is that this relationship is not it's not a safe relationship, because for the first few values, everything is going to 2, 3, and these values appear in the product table. But what about the last two? We have 4, we have 5, and there is no product named 4 or 5 in the product table. So Power BI is in trouble now because the relationship is invalid, and it needs to decide what to do. So what would be the next step? How can it work if the relationship is not valid? There are a few options here. The first one, the one that was used in multidimensional, is to reject the model, saying, you know what, the relationship is invalid. I don't want you to process this model because an invalid relationship is only going to create you problems. That was a very strong assumption that can no longer be used because in the self-service BI world, invalid relationships are an everyday job. We always have invalid relationship everywhere because people load data from everywhere. They do not do any kind of cleaning, and so invalid relationships are there. So taking for granted that we need to use invalid relationship, when I slice by product, what is Power BI supposed to do? So if I slice the amount by product, should I see this $30 or not? Well, theoretically, I shouldn't see them because they are not referenced by any product. But Power BI cannot hide those values because otherwise that would mean that depending on the dimension I use to slice my fact table, I would obtain different results. If I slice by product, I see a number, and if I slice by customer, I see a different total. That is not acceptable. So the only way to solve this problem is to extend the product table with an additional row that contains blanks everywhere. This is what we call the blank row. It's a row that is automatically created by Power BI. It is part of the data model. So it's really there. It's created as a new row in the data model. And then all the rows that have invalid values are related to the blank row. Now, the blank row might be there or might not be there. It depends. It depends on the quality of the data. If the relationship is correct and there are no mistakes, the blank row will not be there. If, on the other hand, the relationship is invalid, then the blank row will be there. That basically means that every time you reprocess your model, the blank row might appear or disappear depending on your data. And you need to be aware of the presence of the blank row because there are functions that consider the blank row as a valid row, and there are functions that do not consider the blank row as a valid row. So using the correct function and knowing that the blank row exists is important in order to compute correct numbers. And I want to show you that with a simple demo. Look at this model. It's our usual Contoso data model. We have sales, we have a date, customer, but I'm not interested in any of those tables. I'm actually interested only in product. So we have sales, product, and a one-to-many relationship linking product and sales, as we usually do. As of now, the relationship is correct. So all the values in sales point to an existing product. And I can slice and dice my data and get always correct numbers. And I have created a measure that counts the number of products. I only need to find a place I can minimize. Okay. I'm sorry, but I had your face on top of the fields. That was not very useful. So I created a measure here that computes the number of all colors. This measure just does a count rows of all product colors. So it counts all the colors which are present. And I know we have 16 colors. As I said, so far the relationship is working. What if I break it? What if I remove from my data model some products so that there will be sales pointing to no products? I can do that. I can simply go to the data model and remove some product. For example, I can go here and say that I'm not interested in blue products. So I filter all the values that are not blue. Okay, let's do a very simple math together. We had the 16 colors before. I just killed one of the color. 16 minus 1 equals, you have a few seconds to think, 15? No, it's still 16. You see that all color still shows 16 colors, even though I removed one of them. What happened? Well, what happened is that because now we have a lot of products that no longer point, so a lot of rows in the sales table that do no longer have the correct product key, the engine created a blank row and generated a blank color that was not present earlier. We can look at here. I'm slicing by brand right now. I can avoid slicing by brand, and instead I slice by color. And you see that I have a blank color here. Blue does not appear anywhere. There is a color which is blank with 176 products. Now, if I go in my model in the product table, I can go to color, sort it ascending, and you see that the first color is azure. We have no blank color at all. The blank row is not here. I don't see the blank row in my table, but I see it as soon as I run a query. I have 176 products which are no longer referencing a valid product, and they are all merged under the blank color. Now, you need to know about the existence of the blank product, the blank row, because the blank row is taking into account here, we are showing 16, but there are functions that consider the blank row and functions that do not. And using the wrong one is going to generate wrong values. Let's get rid of this visual for now. And let me compute a very simple average. I'm interested in knowing the average sales per product. So I can write average sales, and I do an average X over product of sales amount. Now, the question for you is this average X considering or not the blank row? Because if it is considering the blank row, then it will use this value. If it is not, it will not use this value, and the average will be slightly different. Now, if I do an average X in this way, and I project it in my report, then we format it as a decimal number, you see that we obtain some values. So for different colors, we have the average sales, and we have the total 13,674. And the question is this number correct or not? Well, as usual, the answer is it depends. In our specific case, it is not, because you see we have a blank for average sales in correspondence of the blank color. So this amount divided by this number is not producing any number, and it is not being considered at the grand total. The reason is product, in general, a table reference, does not consider the blank row as a valid row. If you want to take into account the blank row, you cannot just reference product, you need to reference values of product. So we can build another average. Let's call it average sales 1. Well, instead of iterating over product, I iterate over values of product. Values guarantees me that not only product will be scanned, but product and the blank row if present. So I can create a measure, format it as a decimal number, put it in my report, and you see that the number is different. Color by color, it's exactly the same value, but at the total level, the two numbers are different. And I see 2 millions as the average sales for the blank row. Again, the question is this number correct or not? And again, the answer is no, it is not. Because there is not only one product that sold 2.4 millions, it's 176 products that sold 2.4 millions. But I have 176 product keys in the sales table that are referencing a blank row. So a calculation like an average is already challenging. The best way to compute this average is not to use any of these, so not use an iterator at all, but compute the average, let's call it correct, where I divide the sales amount, by the distinct count of sales product key. This guarantees me that at the denominator I will have 176, so the number of product keys and not the number of products. Again, let's format it as a decimal number, then we put it here. And now you see that we have this average, which now is correct, and this number, which is different than the first and the second one, is the most correct. It's not perfect, but it's the most correct version of the average. So you see that the presence of the blank row changes the way you compute your values. If you are aware that the blank row might be there, then you pay attention to using the values, to use this thing to compute the counts from the correct table, where you will find that the best approximation of the number you want to use. Of course, if the relationship is working, all these numbers will be the same. So we can easily go to transform data. We remove the last step where we remove the blue products. And if I close and apply, you will see that now all these average will become totally identical. So if the relationships are correct and working nicely, you will have no issues at all. But as soon as a relationship is wrong, you are in trouble, and you need to be aware of that. You have basically two options. You don't care about the problem, and at that point you will have to wake up in the middle of the night when the customer calls you because the numbers are wrong, or you are aware of the problem, you pay attention to the details, and you use the correct function. Now let's go back to the slides and jump to the next one. As you're going to see, I don't use slides a lot apart from the title. The second topic.
Alberto?
Yes?
We have a question by Razi. You can check the Q&A.
Yes, if only I know how to do that. Let me discover that. Q&A, there it is. How can I control the blank row values? For example, if my reference table doesn't include the product ID, I will want the name of the product to be unknown. Oh, that is very easy to answer. You can't. There's no way you can check the presence of the blank row. The blank row exists if the relationship is invalid. If you have values in your reference table that do not include any product ID, then what you should do is add an additional step before loading data in Power BI, where you check this issue. And if you want to show some value, you create a new product in the product table, you mark it as unknown, and you load data in all the attributes. You typically write unknown, missing values, or wrong values, whatever you want. So you generate the the missing product so that it will no longer be missing. And at that point, from the Power BI point of view, there will be no blank row because the relationship is valid. And during ETL earlier than that, you guaranteed the validity of the relationship. This is the good habit we had, we old guys had in the good old times of data warehousing. Nowadays, with Power BI and self-service BI, either you do that in the self-service world, but it's kind of harder to do, or you need to handle the blank row. Okay, let me close this window. Okay, let's talk about dependencies. And it was a very good thing that you warned me because I had no idea that there was a question. So if it happens again, you can stop me at any time.
Sure, sure.
Okay, another topic where relationships hide some complexity is when they create dependencies. If you ever created calculated columns and you played with calculated columns, calculated tables, you might have spotted the circular dependency error when creating relationships. And this is kind of a complex topic to think at. And again, I don't want to spend time looking at the slides. I prefer to show you the problem with the demo. Okay, this is the same model we had earlier. We have sales, we have product, we have data. But now what we want to do is something different. What I want to do is do an analysis, perform an analysis about my sales, slicing by the net price. Now, I have already my matrix. I can get rid of the brand, and I have in the sales table, I have my net price, so I can take the net price, put it on the rows, and the result is not really sexy because you see, I'm slicing by individual net price. A report like this is nearly useless. It is splitting too much of the data and I cannot get any kind of insights from there. So a good thing would be creating a table that I already have, which is the price ranges table. Unfortunately, it's a bit small, but we can enlarge it a bit. Too much. No, we keep it that size. I cannot make it larger than that. You can create a table that contains very low, low, medium, high, very high, and then the minimum and the maximum prices. So my goal will be to aggregate all the products that have a price in between these two values and show it under the very low bucket. The problem of this table is that it has a key. We have a price range key, but if I put it here beside my sales table, there is no column in sales that I can use to build the relationship. Here in sales, I have the net price, but net price cannot link neither to max nor to min price because I want to do some sort of between join. I need to find the row in price ranges which includes the net price. And I have no other column in sales that let me build the relationship. Now, even though it's true we don't have such a row, we can compute it. I can create a new column that computes the value of the price range key in the price ranges for the only row in price ranges where the minimum price and the maximum price include the current net price. So we can do that. It's just a calculated column, and I can go in sales and create a new column here. Home, new column. Let me increase the font a bit. Okay, let's call it price range key. How can I compute it? Well, I need to compute something. Before computing whatever, this will be a different expression later. For now, I just put one for syntax. If I filter the price ranges table to show the only row that includes the current net price, then the price ranges table will show only one row. And once it will show only one row, I will take out of that table containing only one row the value that I'm searching for. So if I place a filter on the price ranges table, where the price range minimum price is greater or equal sales, net price. Minimum price should be less or equal. And the price range is maximum price greater than sales net price. Once this calculate applies this filter, the price ranges table will show only one row. Now, out of a table containing only one row, I can extract the values of the price range key. Values would return a table containing a list of values, but in the very special case where I guarantee that there will be only one row and one column, DAX can automatically convert that table into a scalar value, so the value contained in that table, and provide the result. And this price range key column just works. You see that I have one. Do I have only one? No, I have 1, 2, 3, 4, 5. Somewhere I will have different values. So I now have my price range key. I computed a column containing the value that I want, and then I want to build a relationship. So I have price range key here. I have a price range key here. I can simply drag and drop and build the relationship. Unfortunately, this doesn't work because you see that I get an error that says a circular dependency was detected, and then Microsoft, for whatever reason, likes to show useless strings like this UID, which are the idea of the relationship being created, completely useless. Here, the important thing is only that we obtain a circular dependency error. What is a circular dependency error? Well, a circular dependency happens when you have two entities, two columns or two tables that depend one from the other. So, for example, if you compute a percentage based on a value and then that value based on that percentage, you create a circular dependency. But in our case, we are not changing the DAX code. We only created a relationship. So we need to understand better what are the chains of relationship, the chain of dependencies in this data model. Let's go look at the code of my price range key. Price range key depends on price ranges, depends on the price range key in price ranges, on the minimum price, maximum price. So price range key depends entirely on the entire content of the price ranges table. Depends from has a very clear meaning in DAX. Depends from means if any change happens in the price ranges table, I will need to recompute this column. That is clear. I mean, if I change my price ranges table, I need to recompute the price range key. That's pretty obvious. But why is that if I build the relationship, so if I try to create this relationship, the existence of the relationship creates a dependency between price ranges and the price range key, so that dependency goes circular. The reason is what we have seen a few minutes ago, the blank row. What happens if price range key includes a wrong value? If price range key might contain a value that is of price range key which does not appear in the values 1 to 5 which are in this table, then the engine will need to add to my price ranges table the blank row. So the content of price ranges will depend on price range key. And at the same time, price range key depends on price ranges. That is why creating a relationship builds a circular dependency, because a relationship actually creates a dependency between the target table and the source table for the blank row. There's a slide that shows that, which might be useful to look at. So, price range key depends on price ranges, and that dependency exists because of the DAX code. But if we create the relationship, we create another dependency of price ranges from sales, from the price range key, because of the blank row. Now, if the Microsoft engineer didn't think about that, we would be in trouble. It would be impossible to create a relationship based on calculated column. Luckily, they thought of that. And so they created two separate chains of dependencies. One is the dependency from the DAX code. The other one is the dependency because of the blank row. And as long as you guarantee that the two chains do not cross each other, then you are safe. In order to make sure that the two chains do not cross each other, you need to make sure that the expression you use in the definition of price range key does not depend on the presence of the blank row in price ranges. Now, where is the dependency on price ranges? Here we are iterating over price ranges, and we know that this filter, being an iterator that iterates a table, does not consider the blank row. But here I'm using values, and values returns all the values of the price range key column, including, if it's there, the blank row. Instead of values, we should use a function that performs the very same operation but guarantees never to return the blank row. And this function is distinct. Distinct does exactly what values does, the only difference being that distinct will never return the blank row. If I hit enter, nothing is going to change in my result. It will still be the same, but having used distinct, I can now take price range key and build the relationship the right way. Why that? Because now price ranges depends for the blank row from sales, and sales depends for the DAX code from price ranges. But the two chain of relationship do not cross. Therefore, I can get rid of circular dependencies quite easily if I only pay attention to the blank row. And now that I have done this job, I can just get rid of this net price, take my price range, drop it in my report, and I'm slicing sales amount by price range, where all the sales under the very low are grouped together. Again, the blank row in a relationship is the most common cause of circular dependencies. So knowing that it exists, knowing how to avoid it is the easiest way to get rid of circular dependencies and being able to build calculated relationships that are relationships based on calculated columns. So you see that the blank row is very well hidden, but when it appears, it's kind of a problem. And knowing it exists is not something that you use every day, but it's the kind of knowledge that, when needed, really saves your life. Well, maybe it doesn't save your life, but for sure makes your life easier. Another topic that I want to talk about is ambiguity. Ambiguity happens in a model whenever you create multiple paths between any two tables. And even though you probably never called it ambiguity, I'm pretty sure you already have seen ambiguity somewhere. Look, for example, at this model. Here I have in the sales table, let's create a new chart where I only put sales and date. Okay. Right now, this relationship is working fine because the model is non-ambiguous. Non-ambiguous means that between date and sales, there is only one path, one and only one path. So a filter on date will be moved to sales following this path. Now, can I create multiple paths between tables? I can. Right now, this relationship is based on the order date, but I can make another relationship based on the delivery date. The engine let me create it, but it marked it as inactive. Why that? Because if both relationships were active at the same time, that model would become ambiguous. Ambiguous means that a filter on date has multiple ways of being transferred from date to sales. And not knowing which of the two paths to take, the engine would be in trouble. In order to avoid the problem at all, the engine lets you create only one active relationship. The second one will be created inactive. Now, we delete this relationship because that's not what I want to show you. It's pretty obvious that you cannot create multiple relationships between any two tables, and only one of them can be left active. What is not obvious is that ambiguity might appear in a model for other reasons, and it's not always evident. Let's look at this model a bit deeper. We have sales, product, and data. This is the same tables we had earlier. But then I added another table, purchases, which is related to product and to data. It's not related to customer because purchases are not tied to customers, but it's tied to product and data. And there's nothing strange. This is nothing but a double star schema, one star schema between sales, product, date, and customer, and another star schema between purchase and product. So everything is working fine. But if I deploy this model and give it to my users, they will start complaining at some point. I built this report. As you can easily see, I'm not very good in building reports, but I'm interested in the behavior of the report, not in it being nice. In this report, I'm filtering the name, the customer name, the product color, and then I have a brand and sales here. Now, if I click on Adam Jordan, you see that Adam Jordan only bought Contoso and Southridge Video, whereas Stephanie Adams, same stuff. Alexander only bought Northwind Traders. Whenever I filter something on the customer name, the brand and the sales get filtered, but the color does not. So I have no idea what are the colors bought by Stephanie. Maybe she bought all the colors, maybe she didn't. But the filter from the name does not reach the color. Let's check that this is correct. A filter on the name is in the customer table. The filter from customer goes from the one side to the many side and it reaches sales. But then from sales, it cannot propagate to product because that is many to one. And the filter context does not propagate many to one. It only propagates one to many. So the behavior of my slicer is correct. It is what Power BI would expect, but well, my users would probably not love it because they would like to see the slicer only showing the color that Stephanie bought. So there's an easy solution to that. We learned that we have a cross-filter direction. This arrow is what is preventing the filter moving from sales to product. So I can just double-click on it, go to cross-filter direction, and make it bidirectional. As soon as I click OK, you see that this arrow becomes bidirectional, and my report starts working the way I like. If I filter Stephanie, I only see the two colors that she bought. And if I filter Aidan, I see the only color he bought. Eduardo bought a different color, and so on. So a filter on the customer is propagated to the product and then to the sales table. Looks like I did a great thing by enabling bidirectional filter. And the model is still safe. Keep in mind, if for whatever reason I enable bidirectional filter on too many relationships, the engine complains about the fact that by enabling bidirectional filter on too many relationships, the model is now becoming ambiguous, because a bidirectional relationship can be traversed both ways. Therefore, ambiguity might appear earlier. But the engine didn't complain about anything here, so I can assume that the model is not ambiguous, right? Unfortunately, wrong. The reason is Power BI does not consider this model ambiguous, even though the model is ambiguous. Focus on date. Starting from date, we can filter sales straight, and that's fine. And we can filter purchases straight. But there is another path that we opened by enabling this bidirectional cross filter, which is date filtering sales, then sales propagating its effect to product, and finally product filtering purchases. So there are actually two ways of moving the filter from date to purchases. One step only, one that requires 3 steps all around the data model to reach purchases. And this model is ambiguous. It's not a safe model. Nevertheless, Power BI did not complain about it. Why that? Well, if you were Power BI, you would probably know having a choice between a relationship that is only one step and a much longer trip that requires you 3 jumps to reach a table. Which one would you choose? By no means I'm gonna traverse 3 relationships when I can jump only through 1. So Power BI prefers this relationship and therefore does not consider the model as ambiguous, even though it is ambiguous. You can trust Power BI, meaning that the algorithm that detects whether a model can be disambiguated or not is quite sophisticated, but it usually works. But unfortunately, at least in my opinion, it's just too powerful. It lets you work with data models which are completely unsafe. And I want to show you that. Again, I want to use the slides for that because we have this model. This is the same model we have seen earlier. And we have two relationship linking purchases and date. One is straight, and the other one traverses three relationships, but both are legit, both are valid. So in this model, let me get rid of that part. I want to ask you a few questions. The first one is, does date filter sales? And the answer is obvious. Date filters sales because there is a direct connection between the two. That was easy. Does customer filter purchases? That requires a bit more thinking. Customer filters sales, sales filters product, product filters purchases. Therefore, yes, customer filter purchases because there is a long chain of relationship that connects a customer and purchases, and all of them can be traversed because of this bidirectional cross filter. Another easy one. Does date filter purchases? Well, actually, it can do both ways. It can filter straight, and it can go the long way, what we have seen earlier. So there are actually two ways of filtering purchases, and we know the engine will prefer the shortest path, this one against the longer one. So far we haven't seen any real issue. The problem is the last question. Imagine that I build a report that contains a column from the customer and a column from date. So it's filtering customer and it's filtering date. And then I aggregate the sum of purchases. Which subset of purchases will be filtered by sales? Customer filter sales, sales filter product, product filter purchases. But the problem is that sales fills two filters, one from customer and one from date. And date is also being used directly to filter purchases. So which portion of sales will be used to move the filter from customer to purchase? The one that fills the filter from date, or it will not fill the filter from date because the filter from date is being used already here. So this relationship will be disabled. The engine needed to disambiguate the model. It needed to enable or disable relationship before running the query. So the thing is, it either disables this relationship, or it disables this relationship, or it finds another way of computing the value. Now, the first time I saw this behavior, I thought, well, it will probably disable one of the two relationships. It's only that I don't know which one it will disable. So I discovered that. I create one measure that kills this relationship, the one between date and sales, and I create another measure that kills this relationship, the one between date and purchases. So to force the engine to go one path or the other. And then I build a third dimension that uses the model as it is. And my expectation was that of the three measures, two would be identical. And that would give me the information about which of the two relationships is being enabled or disabled. And that's exactly what I did in this report. I created a few measures. So under sales, no, product, purchases, okay. I created one measure that disables the relationship between date and purchases, and another measure that disables the relationship between date and order date. So one disables the long path, the other one disables the short path. And then I have the third measure that just computes the sum. And I created a report. Now, this report is interesting to see, not because of its content, but you only need to focus on the numbers, quickly look at them, and discover that they are all different. The standard model does not compute the same value as when one relationship is disabled or the other is disabled. It computes a third value. And some numbers are identical. This number is identical to this one, but the total, the individual rows here are all different here and there. And they have nothing to share with what we see here. So what is this report telling us? The report is telling us that when the engine needs to move a filter from date to purchases, it only filters using this path. But if there is also a filter from customer that goes through sales, sales will fill the filter from date and from customer. Therefore, date is being used twice, once to filter purchases straight, and once to filter sales to move the filter up to purchases. The problem is not understanding these numbers, because the problem is that I don't want to even think at these numbers. Basically, I would not trust such a model to go in production, because if a customer asks me, how did you compute those values? The only reasonable answer would be, I have no idea. Power BI computed them, but I actually don't know exactly what happened there. And the problem is because we created an ambiguous model. Power BI didn't warn us, but we introduced ambiguity in the model, and ambiguity might generate really hard to explain values. Besides, keep in mind that this model only contains 5 tables. So 5 tables, pure star schemas, 1 bidirectional relationship is enough to introduce ambiguity and make the model unpredictable. In the real world, things are a bit more complex than that, because in the real world, you have many more than 5 tables. I was happy because the first time I presented this topic, an attendee at the conference came to me saying, hey, I'm having trouble understanding the result of my model. And I say, okay, show me your model and let's discover where the problem might be. And this was the model. I actually took a picture of the data model at the time, and I just started counting the number of bidirectional relationships that were present in the model. If you count them, you will quickly see that this model is ambiguous. I have no idea where ambiguity is, but for sure this model has a lot of issues. This model basically computes whatever you want. You ask a number and that number comes out without you knowing how it came out of the model. Besides, some of these bidirectional cross-filters are not that dangerous. This one, for example, at the end of a chain of relationship is not that bad. But this one in the middle of a lot of chain of different relationships, that can do any sort of damage. You have no idea what's going to happen because of that bidirectional cross-filter or because of this one. The relationship goes here, then goes here, then goes here, and then goes back to the original table. That's also a loop. The fact that Power BI can work with this model doesn't mean you need to work with this model. So whenever people tell me that they want to use bidirectional relationship, I always say you can't. There's no way you should not use BiDi at all. If you really want to use bidirectional cross-filter, then you can try to do that. But just be warned that ambiguity is around the corner and you might have issues because of that. So ambiguity is not always evident. Keep in mind, 5 tables and it's already hard to find. 100 tables, there's no way a human can find ambiguity. To me, Power BI should be much stronger than that and prevent us to use any kind of ambiguous model. Unfortunately, that would prevent the usage of bidirectional cross-filter nearly everywhere. So bidirectional cross-filter is bad. Don't use it just because it looks nice. There are other ways to solve the same problem, much better, much easier to use, that do not produce wrong values. And use bidirectional cross-filter only if you know what you are doing. Otherwise, stay away from it and your life will be so much simpler. The last topic that I want to cover is weak relationships. A relationship can be a strong relationship or a weak relationship. But first of all, what is a weak relationship at all? Well, in the good old days, you could create Power BI data models by loading data from SQL, from Excel, from wherever you wanted, and you created tables in the Vertipack data store, basically loaded tables in the Power BI model. that we now call the vertical continent. So you load some tables and you build relationships between tables in the continent. Life was easy. All the relationships were strong. You still had bidirectional cross filter, but that was the only enemy. Now, since the end of last year, they introduced composite models. In composite model, you can mix in the same Power BI model data loaded from Vertipack with data in direct query. I don't know how familiar you are with direct query. With direct query, you do not load data in Power BI. You only link to an existing SQL Server database so that the engine will run SQL queries whenever it wants to gather data from the data source. So data is not loaded in Power BI, it's just linked. What is the problem of linking to data? Well, you can create an island, so different dataset islands which are different direct query connections. The problem of direct query is that the engine cannot make any assumption on the content of these tables. It never sees the real content of the tables. It only knows there's a table with some data, but there's no way it can guarantee uniqueness of values and that if you build a relationship between these tables, there will be a primary key and many sides, or one side, cross-filter direction. None of that can be guaranteed by the engine because the engine does not have access to the actual data. So, in order to make relationships between datasets and the relationship between different islands possible, in the engine they needed to add a logic, so to make the code more complex, to be able to handle scenarios where the uniqueness of one side of the relationship was not guaranteed. So you need to be able to build a relationship between two tables, not knowing that the column used for the relationship has unique values on the one side of a relationship. These relationships that go cross-island, are known as weak relationships. Why are they weak? Because no table expansion happens, no blank row enforcement is made. The engine does not know about the validity of a relationship. It does not know whether all the values are present or not. Therefore, there is no blank row enforcement, there is no table expansion, and this is what we call a weak relationship. Once the logic for weak relationship was in the code base, so it was in Power BI, they thought, well, now Power BI can handle weak relationship. Let's make it possible to create weak relationship also inside of the continent. And weak relationships are generated whenever you create a relationship between two tables and the column you use to link the two tables does not have unique values in neither the tables. Let's see that together. To do that, I have a fourth model. Oh, here it is. Which is again our usual model. We have sales, customer, product, and data. And then I have created a budget table. What is the content of the budget table? Well, budget basically contains budgeting information. So the budget contains a country, a brand, a scenario, and the budget. It does not contain individual products. It contains the brand, because you never do the budget at the product level. You do that at a much higher level. So you say, well, for this brand in China, this is the amount that I expect to sell. And having only the brand and not the product key makes it harder to create a relationship between the budget and the product table. Because if I create a relationship between, if I want to create a relationship with product, I don't have a product key in budget. I can create the relationship based on the brand, but that would be a weak relationship. And this is coming with some issues. Let's first see what happens if I don't create a relationship. Well, if I don't create a relationship, if I slice by product brand, I see some values. I see the value of the budget, and you see that it is never sliced because product brand does not filter budget. Product brand is here, budget is there, there's no relationship, so there's no slicing happening. If I slice the same value by budget brand, then I see the budget correctly. The same would happen if I add sales amount. If I slice sales amount, I would be able to slice it by product brand, but I will not be able to slice it by budget brand. So what I want to do is build the relationship. And thanks to weak relationship, I can do that now. I can take brand, link it to brand, and Power BI is not really happy. You see, it does not just create the relationship saying, hey, go ahead, you can do that. It creates the relationship, but it warns me. And it says it's kind of small here. Let me see. We know I cannot zoom, so. But the error message says the relationship has cardinality many to many. This should only be used if it is expected that neither column contains unique values. And that is exactly what we know. And most important, that the significantly different behavior of many-to-many relationship is understood. So basically what it is saying is, if you understand something that I am not going to explain you, then you can go ahead. But if you don't understand what I'm talking about, you better step back. Now, what do you do when you see a warning yellow message that you don't understand? Of course, you click OK. And that generates a many-to-many weak relationship. It is weak, we know it's weak because both sides of the relationship are the many side. Again, it's not a many-to-many relationship, it's a weak relationship. Weak relationship means that the blank row is not generated and the table expansion doesn't happen. But what is important here is that the blank row does not get generated. So if I just look at my report, everything looks fine. Now you see that product brand slices my budget and budget brand slices the budget the right way. And all these numbers are totally identical. So it's working nicely. But what happens if I remove from the product table one brand? Let's say that I remove one of the brands, same as I did earlier, to break my relationship. I can go to transform data and remove one of the brands. So I go to brand, let's remove Contoso, and I do text filter, or what is not equal to Contoso. Now Contoso will no longer be a value in product brand. Now, if you look at those numbers, you will see that there will be no blank row under the brand, and all the numbers are identical to before. So if you compare Adatum, AdventureWorks, Fabricam, Litware, the value is the same that we have here. Only that here Contoso is missing and here it is not. Which basically means the sum of this column is 39 millions. The sum of these values is less than 39 millions because Contoso is not here. Because this is a weak relationship, the blank row has not been generated. And depending on the column that I used to do the slicing, I obtain different values. This is bad. This is really, really bad. And it's not wrong. It's, I mean, you cannot blame Power BI for showing those values. There's no other way it can work. Not being the blank row, there is no place where it can show the value. So at the total level, the number is correct. Row by row, those numbers are correct. The problem is that we use bidirectional. We used a weak relationship without properly understanding what we were doing. Using weak relationship has, again, a lot of issues. They are slow, they have problems in terms of calculations because they do not generate the blank row and they cannot enforce the uniqueness of the values. Therefore, is it good to use them? Absolutely. If you know what you're doing, weak relationships are extremely powerful. Yes, they are slow, but you can avoid that. Yes, they do not generate the blank row, but you know that and you use them for what they are, and you can create great models. Using them without knowing what you are doing is kind of the easiest way of creating issues to your reports. So, that goes to the conclusion. Relationships come with a lot of properties. Standard, strong, one-to-many relationships, they are easy. They are fast, they are safe, they always produce correct values. They have some limitations, but these limitations are for the best because they keep you in a sense. As soon as you use features like bidirectional cross-filter, weak relationships, or calculated relationships, that you are entering a dangerous zone where either you have the knowledge needed in order to travel correctly, or you might easily create issues because you do not understand exactly what happens. That is not a suggestion not to use these features. This is a suggestion to study this feature very well, understand very well what relationships are, because all these are powerful features, and knowing how to use them lets you build a better model and get better insights from your data. And that is the last slide. So time to tell you a big thank you if you had the patience to listen to my voice so far, and give back the voice to Shlomi.
Okay, thank you very much, Alberto. It was awesome. A lot of issues that I been familiar with. אם למישהו יש עוד שאלות לאלברטו ולגבי מה שהוא הציג, אתם מוזמנים עכשיו לרשום או ב-Q&A או בצ'אט. אני חושב שזה היה אחד הוובינרים הכי מעניינים שאני עברתי לאחרונה. בן אדם תותח. כן, תהילה, תודה רבה. Alberto, תהילה, thank you for clear and helpful.
Thank you.
אם למי שיש עוד שאלות, זו ההזדמנות באמת להביא אחד התותחים הגדולים בעולם בתחום הזה לוובינר. באמת זה לא היה פשוט. Okay, so I want to thank Alberto. Thank you very much for joining me to the webinar. It was really wonderful. I see there is no question so far, so I want to thank you. Good evening.
Thank you. Have a good night all.
Thank you. Good night. ערב טוב לכולם. והוובינר הזה יעלה בערוץ פאוור ישראל. ההקלטה שלו תעלה אם לא היום אז מחר, ונתראה בוובינר הבא ביום חמישי, אני חושב הבא, או יום שלישי הבא. תעקבו ביוטיוב. ועד כאן אני רוצה לסגור את השידור. אני שלומי, חברת יוניק. אתם מוזמנים לפנות אליי בכל הערוצים. Thank you again, Alberto. Keep safe. And yeah, and I hope for better days. And maybe
we will see in person.
Yeah. I hope in Israel soon you will come. Okay. So goodbye and good evening to all.
Thank you. Good evening.
Bye bye.